Hello, everyone. So we know how to differentiate a function at one point a, right? It was f prime of a is the limit as h goes to 0, f of a plus h minus f of a, all divided by h. But depending on what point a that we're trying to find the derivative at, sometimes it might exist and sometimes it might not exist. And if it does exist, hopefully we can compute a formula for it. So this was point by point, but if we put that all together, then we get a new function which is called the derivative function that we can think of all at once. So that's what we're going to start to talk about in this short video. So here is basically what I said. If we start with the function f, then we can compute a new function f prime, which is called the derivative function. And it's defined by this formula. So remember, a function is just a rule that maps an input to an output. So if we input a point x, here is a formula for this new output, this new function f prime of x. It's the limit as h goes to 0, f of x plus h minus f of x divided by h. So basically, take the derivative at the point x. And so this is a perfectly nice formula, provided the limit exists. So the derivative function, this f prime, the domain of this function is the set of all values x for which the limit exists. So sometimes that might be smaller than the domain of the original function f. Sometimes it's the same, sometimes it's smaller. And okay, what does f prime represent? So f prime represents the slope of the graph of f at x. So typically the graph of f will tell you something about the graph of f prime. Remember, f prime is now its own function. It's a new function. It's different to the graph of f, so it's not going to look the same, but there is a correspondence between them. So for instance, f prime, remember, represents the slope. So if we know that the graph of f is going up, then f prime has to be positive, right? Because f has to have positive slope. Or if the graph of f is going down, that means the slope is negative. That means f prime must be negative. So knowing one often helps to sketch the other. And there are these problems that we like to torture you with, where we give you some graphs and say match up the graphs of f and f prime. So we have to be a little bit careful. So let's see some examples of those. So here on the left, we have a graph of some function f of x, excuse the picture. And on the right, I claim this is a reasonable graph for f prime of x. So why do these look reasonable? What points do I want to draw attention to? For instance, in the graph of f, we see that to the left of -1, the graph of f is going down, which means the slope is negative. And then that's also reflected in the graph of f prime, right? That the graph of f prime is negative. The y values are all negative to the left of -1. So we have to match up the slopes of f correspond to the values of f prime. Okay. And then similarly, between -1 and 1, the graph of f is going up. So the values of f prime are going up. So f prime doesn't increase at the same points that f increases. Notice that f is increasing all the way between -1 and 1. F prime is only increasing from -1 to 0. So the increases are not the same. But we can say that when f is increasing, f prime should be positive. And then similarly to the right of 1, f is going down, the slope is negative. That should mean f prime is negative. Okay, that's reflected over here. So we have to be a bit careful in matching up the pairs and try not to get too confused. Here's another graph with a function g and its derivative g prime. So here, g is going up at a constant rate to the left of -1, right? It looks like a line. The derivative should be constant. The slope should be constant, and we see that. But then at -1, the direction, the slope abruptly changes from going up to going down. So at -1, there is no well-defined tangent line, right? If you were to try to compute the derivative, the right limit will catch the -1, the left limit will catch the +1, the two-sided limit doesn't exist. It's not going to be differentiable there. And we see that reflected at -1 for g prime, right? G prime is not defined at -1. G prime of -1 does not exist. And then similarly, g has constant slope going down between -1 and 1, which we see for g prime. And then g has constant slope going up to the right of 1, which we see for g prime has value 1. Okay, so here, for instance, the domain of g was, say, the entire real line, or -1, everything that was on the picture. And the domain of g prime excluded -1 and 1, right? So the domain of g prime can be smaller than the domain of the original function g. Okay, let's see a similar idea with formulas. So let's suppose f of x is a square root function. Okay, that's defined for all x bigger than or equal to 0 because we're not allowed to take square roots of negative numbers. Let's try to compute the domain on a formula for f prime. So the only thing we can do until we get some more high-powered tools is to go back to the definition. So let's try to apply the definition. And remember, that was, how do we compute f prime of x? We fix point x and we try to compute f prime. That means we have to look at the limit as h goes to 0 of f of x plus h minus f of x divided by h. And if you try to naively, plug in h equals 0 straight away, whenever you're computing derivatives, you cannot start by plugging in h equals 0 because you will get 0 on the top and 0 on the bottom. So you always have to do some kind of algebra first and hopefully use some tricks or do some kind of algebra to simplify. So in this case, f of x plus h is the square root of x plus h. F of x is just square root of x. So we have to simplify this. It's got square roots in, so let's rationalize the numerator. We multiply top and bottom by the conjugate. If you expand everything and cancel the h's, hopefully you can trust me that we're left with 1 over the square root of x plus h plus square root x. And then if we let h go to 0, this goes to 1 over 2 square root x as h goes to 0. And this is all great provided x is not equal to 0. So if x is equal to 0, then 1 over 2 square root x does not make sense. Okay, so this computation is valid if x is bigger than 0. What if x equals 0? Then we have to go back to the step before we took the limit. So if we look at 1 over the square root of x plus h plus square root of x, if x equals 0, this becomes 1 over the square root of h. And as h goes to 0, that will approach infinity, as h goes to 0 from the right. So in that case, the limit does not exist. So the limit does not exist when x equals 0. So there is no derivative at 0. There is only the derivative for x strictly bigger than 0. Okay, so we computed f prime of x is given by this formula for x strictly bigger than 0. It doesn't exist for x equals 0. So the domain is x strictly bigger than 0. So the domain in this case of f prime is again strictly smaller than the domain of f. So here's the same thing, the same example, just in a picture. So we had y equals the square root of x for x bigger than or equal to 0. So included the point 0. And then we computed that this was the derivative for x strictly bigger than 0. It's not defined at 0, as we can see on the graph. And the square root function is going up as x increases. So we expect the slope should be positive. And that we see on the derivative, right? The derivative lies above the, lies above the x-axis. It's a positive function. And then also the graph of the square root function it's going up, the slope is positive, but the slope is becoming less and less positive, right? It's less and less steep as time goes by. And we see that on the derivative, right? The derivative is becoming smaller and smaller as time goes by. So the original function is not changing quite as much as x gets larger and larger. So we can see a lot of things if we compare the graph of f and the graph of f prime, but we have to remember to translate, right, between the two different languages. If the graph of f is going up, that does not mean the graph of f prime is going up. If the graph of f is going up, then the graph of f prime is positive. So don't let it trip you up. Okay, another important thing to keep in mind is, since we're going to be asking you these questions of when is a function differentiable, if it is differentiable, work out the derivative. Something that's useful to know is if f is differentiable, then it is continuous. So being differentiable is stronger than being continuous, but you cannot go backwards. So continuous does not imply that you are differentiable. And another really useful way to think about this is to say that if f is not continuous, then it is not differentiable. Okay, so differentiable implies continuous is the same thing as saying not continuous implies not differentiable. So this is something called the contrapositive. So a statement that looks like A implies B, so some statement A, some statement B. A implies B is equivalent to not B implies not A. It's not the same as B implies A. For instance, if A is that A is a statement that it's the weekend, B is a statement you call your family. If it's the weekend, then I call my family. That's the same thing as saying if I'm not calling my family, it's not the weekend. It's not the same thing as saying if I call my family, then it's the weekend, because you could call your family on other days. So it's often useful, so that's the contrapositive. But for now, remember, differentiability is stronger than continuous. So if I'm differentiable, then I'm continuous. If I'm not continuous, then I'm not differentiable. So this is useful, for instance, because if you see that a function is not continuous, then you can say straight away it's not differentiable without doing anything else. So that can save you some work. And as I said, order matters. For instance, absolute value x, it's continuous at 0, but at 0 it has that corner, so it's not differentiable. So continuity is weaker than differentiability. Differentiability is harder. And another example, for instance, if f of x is 1, if x is strictly bigger than or equal to 0, is bigger than or equal to 0. F of x is 0 if x is strictly less than 0. So it kind of has a jump. It starts with 0 and then it jumps up to 1. Clearly, this is not continuous at 0 because the right-sided limit is 1, the left-sided limit is 0. So there is no limit, it's not continuous. So we can say for free from that, just based on the fact that it's not continuous, that it's also not differentiable without making any more computations. So that's a useful fact to remember. If it's not continuous, then there is no chance that it's going to be differentiable. Okay, thanks everyone. That's it for this time. See you next time.